Hello everyone, my name is Qian. I'm a PhD candidate at Hong Kong University of Science and Technology, and I will present our work on make interaction situated, designing user-acceptable interaction for situated ways in public environments. The development of augmented reality has brought data visualization beyond the desktops, integrated into the physical environment to assist people's institute decision-making, such as for renting a house, daily shopping, and for professional training or communication. In these cases, the data visualization shown with a physical or virtual reference in AR is usually referred to as situated ways. When people referring to situated ways in their lives, the interaction plays a critical role that among the user, the physical environment, and the data. Previous work designed interaction techniques for triggering or analyzing situated ways when people were in AR headsets. However, they mainly focus on the interaction design that only consider how people manipulate the physical objects, neglecting that user interaction would be influenced by the social or environmental context around them. HCI researchers proposed a framework about how interactions might hide or reveal manipulations and effects. They divided interaction with systems or platforms based on the spectator experience within a social context. For example, within this framework, the interaction that hide both user manipulation and the effect can be classified as subtle, such as the interaction with cubicle photo booth or personal handheld device. The interaction that is used for artist performance, such as the show by Stellaric, a famous performance artist, is classified as candid interaction, as they present both the manipulation and the effects to other people in an obvious way. For HMD device, such as AR headsets, if we use it in public, the user manipulation is revealed to others, while the interactive interface and the effect are hidden. This may cause suspenseful interaction. Imagine that in a supermarket, you wear an AR glass and raise your hands and wave them in front of a shelf. But in the eyes of other people, you may just clicking and playing with the air. Some people may prefer not to behave like that in public. So it is necessary to design and develop interactions with situated ways that consider the social and the environmental context. Previous work in HCI have exploring the design of interactions for public scenarios with AR or portable device. However, little attention was paid to the design of interaction with situated ways and the analytical tasks. In this work, we aim to bridge the gap by considering a broader context that not only involves user and the physical context, but also the social environment around them in public when designing user interactions. To understand the user needs and the constraints of performing interactions with situated ways, we first conduct a formative study in two typical scenarios. In a shopping store and a library, we recruited participants and invited them to perform the routine tasks, like buying a product or borrowing a book. We collect their needs through an on-site interview. Generally, we found that users require the overview that summarizes the data and the detailed view and the comparison view for selected items of interest. The location of situated ways is determined by the required data type and the task. In public environment, there is a clear preference for more subtle forms of input, such as eye-based interaction, hand gesture with minimal movement, and the use of physical objects for interaction. Based on this finding, we first proposed a design space for interaction with situated ways in public. This considers multimodal input modalities, including gestures, eye movements, and input from spatially aware objects. It also incorporates the types of data required and the relevant tasks. Based on summarized the design space, we work closely with 6 users through an iterative design process to design user-acceptable interaction. We first defined and developed the suitable interactive technique for triggering situated waves, and then developed the following analytical interactions. Finally, we developed a system that includes several interactions that match users' needs. Here we showcase these techniques. They were developed by Unity and text in the HoloLens 2 headset to trigger the overview that summarizes the data of a bunch of items or products. When user scans multiple items with their eyes, the system will automatically detect it and take it as an indicator of triggering the overview, and it will present it on above these items. This overview can update automatically based on the tracked items. After that, if the user would like to search one item and a specific category, they can use the eye gazing on the legend of the chart, and then the system will present arrows above the matched items. Next, when interacting with the required detailed view for a specific item or a product, we provide 3 kinds of interactions based on the accessibility of user's hand. First, if user would not like to use their hands, or their 2 hands are occupied, they can use eye gazing to trigger the detailed view. If user has 1 hand available, we offer an alternative way to spatially move the objects to trigger the detailed view. The third method can be used when the user has 2 hands available. They can hold the object and touch its surface to trigger the detailed view and use the edge of the object to interact with the slider to filter the detailed data. All these 3 kinds of methods are provided for users in an adaptive way, which depends on distance between the user and the product, as well as the number of hands detected by the system. We also provide an adaptable interface where user could predefine the specific method they would like to use before entering the system. Next, when interacting with the comparison view, we offer 2 ways of triggering the view. First, the user could easily activate the comparison menu with buttons by holding 2 objects together for detection. Then, to select the data properties, they could use either eye gaze or spatial movement to select one button. After activating the comparison view, the user could filter the data based on multimodal interaction that use their eyes and hands. First, they need to use their eyes for the interest area selection, and then use a subtle hand gesture rotation to conform. This selected area will be highlighted, with data from other areas being filtered out. Based on user requirements, they would also want to adjust the size of the comparison view, so we offered a scaling method by manually changing the distance between the held objects. For example, if user want to enlarge the visualization, they just pull apart these 2 objects. A line showing the distance will appear, and the width chart will be larger when the distance exceeds a threshold. Similarly, the user could reduce distance to zoom out the size of the chart. To evaluate the usability, usefulness, and user acceptance of our proposed techniques, we implement these interactive techniques into AR prototype and conduct a field study with 14 participants in public. We set a baseline AR system which uses hand-based interaction that considers the mid-air gesture and touch as the input. The study results show that the interactive techniques in our prototype were perceived as more useful and accepted by users than baseline. Participants prefer the eye-based interactions and they need to combine their hand and eyes for comparison. I still think they are more acceptable than barely use hand. For more details, please read our paper.